And we have seen some examples also based on fixed points and periodic points, and how to find period of some point of that function also we have seen. Now we will whether anybody has some doubt in yesterday's lecture. So shall we start new definition?
Yes, ma'am.
Okay, so this is not a new definition, but we are recalling this definition, open ball. Everybody may be knowing open ball in real analysis. What is open ball? Let U belongs to Rn and R greater than 0. Then open ball centered at U with radius R. With radius R greater than 0. What is that? It is the set of all points whose distance from U are strictly less than R, right? So is the set which is denoted by BP, center U, radius R, and is given by set of all points V in Rn, which satisfies the property that distance between U minus V is strictly less than R. Right? If it is less than or equal to, then it will be a closed ball. But we want an open ball definition. So set of all points V in Rn for which modulus of U minus V is strictly less than R, which this set comprises as open ball center at U and with radius R. Okay, so there are some definitions. First we will see, then we will go to the theorem. So another definition is stable fixed point. We already seen definition of fixed point. U is said to be fixed point of f if f of u is equal to u. Now what is meant by a stable fixed point? Okay, so let V be a fixed point of f. F is a function from Rn to Rn. Then V is said to be stable. Then V is said to be stable if given any ball B of V epsilon, center V and radius epsilon. There is a ball another ball, we are saying B of V delta, center V and radius delta, so that if U belongs to BV delta, then th iteration of f at U belongs to BV epsilon for t greater than equal to 0. So what is this definition? Stable fixed point. First it should be a fixed point, and then that fixed point is said to be stable provided that given any ball with center V and radius epsilon, there exists another ball BV delta, so that if U belongs to BV delta, then tth iteration of f at U also belongs to BV epsilon for all t greater than equal to 0. Then we say that it is a stable fixed points. So what it means, if points close to V, we are taking open ball centered at V, means points close to V do not wander from V under all iterations of F. Means if we take any point of near to V that do not go far from V under tth iteration of F, that is the meaning. Okay, means they belongs to that open ball only. B open ball, center at V and radius epsilon. Is that okay? What it means? Fixed point is stable means the point close to V do not go far from V under every iteration of F, we can say, because F raised to T at U means what? For T greater than equal to 0, under every iteration of F, they does not wander far from V, means they will belongs to again that open ball itself. Then we say that that fixed point is a stable fixed point. If not, is said to be unstable fixed point. Otherwise, V is said to be unstable. Okay, V is said to be unstable. This is stable. Another definition. Asymptotically stable. We asymptotically stable fixed point. What is meant by asymptotically stable fixed point? So a fixed point V of F is said to be asymptotically stable if it satisfies two conditions. First, it should be first stable. So V is stable. Stable means whatever earlier definition. And extra condition, another condition is there is a ball BVR, open ball centered at V, radius R, so that a tth iteration of F at U converges to V as T tends to infinity for every U belongs to BVR. Okay, so what this definition means? Asymptotically stability requires additional condition. First, it should be stable, and another additional condition is all solution which starts near to V. All solutions which starts near to V means we are taking open ball, we are taking points in U, and we are saying F raised to T at U converges to V, means all solutions which starts near to V converges to V. Then we say that it is asymptotically stable. Is that okay? So asymptotically stable fixed point means first it is a fixed point, then it is a stable fixed point, as well as another third extra condition, additional condition is there exists a ball BVR so that F raised to T at U tends to V as T tends to infinity for every U belongs to that open ball. Okay. Another definition. A periodic point Up to now we've seen what is mean by fixed point is stable and fixed point is asymptotically stable. Now another definition is stable periodic point. Let another definition. Let W be a periodic point of f with period k, of f with period k. Then W is stable. Then W is stable if W, f of W, f square W, and so on, f raised to k minus 1 of W are stable as fixed points of f raised to k. W be a periodic point is said to be stable if W, f of W, f and up to f raised to k minus 1 W are stable as fixed points of f raised to k. Okay, and W is said to be asymptotically stable if same definition, only W, f of W, f square W, f raised to k minus 1 W are asymptotically stable as fixed points of f raised to k. And W is said to be asymptotically stable if W, f of W, f raised to k minus 1 of W are asymptotically stable. As fixed points of f raised to k. Asymptotically stable. Okay, so we have seen the definition when fixed point is said to be stable and asymptotically stable, as well as when periodic point is said to be stable and asymptotically stable. So note that, or remark, in another words, you can do this. A fixed point V is stable if points close to V do not wander, points close to V do not wander far from V under all iterations of f, under all iterations of f. And asymptotically stable and asymptotically stability requires additional condition that all solutions which starts near to V converges to V. Converges to V. Okay, so is all these definitions clear? Let me. Is that okay?
मैम वो asymptotically stable definition है ना, can you repeat?
कौन सा ऊपर वाला क्या फिक्स पॉइंट?
हाँ ऊपर वाला मैम,
ये वाला ना, asymptotically stable fixed point.
ये वाला
So for step it should be a stable fixed point first. Okay, a fixed point v of f is said to be asymptotically stable. First condition is v is stable. Stable means the points which are near to v do not wander from v under all iterations of. Okay, and what is additional condition it requires? There exists a ball. There exists a ball BVR centered at V radius R so that f raised to t at u converges to V. Means all solutions near to V converges to V as t tends to infinity. You can see here for every u belongs to BVR, f raised to t at u converges to V as t tends to infinity. Then we say that it is asymptotically stable. Means first it should be stable fixed point, and then additionally all solutions near to V must converge to V as t tends to infinity. Is that okay?
yes ma'am.
We will see examples also. At that time it will be more clear. So first we will see one theorem before examples. Theorem 4.17, this is. Suppose f has a continuous first derivative. Continuous first derivative. F has a continuous first derivative in some open interval. In some open interval containing a fixed point. Containing a fixed point V. Then we want to prove if mod of f dash at V is strictly less than 1, then V is asymptotically stable. V is asymptotically stable. And B, if mod of f dash of V is strictly greater than 1, then we can say that V is unstable. V is unstable. We want to prove V is unstable. So whenever f has a continuous first derivative, then asymptotically stable and unstability we can check just finding f dash at V. If mod of f dash at V is strictly less than 1, then we say that V is asymptotically stable. And if it is strictly greater than 1, then we say that V is unstable. For if it is equal to 1, we cannot say whether it is asymptotically stable or unstable. We will require another additional conditions to check to say whether it is asymptotically stable or unstable. So in this theorem, we have to prove these two conditions, two statements. Let's start the proof. What is given? F has a continuous first order derivative. So first we will assume that mod of f dash at v is strictly less than 1. Now what is given? F dash has a continuous derivative. So by continuity of f dash of first order derivative f dash, there must exist an alpha. There exists an alpha so that mod of f dash of v is less than equal to alpha less than 1 on some interval I, say it is v minus delta, v plus delta for a delta greater than 0. Okay, so since f dash is continuous, we can say that there exists an alpha so that mod of f dash of v is less than equal to alpha strictly less than 1 on some interval v minus delta, v plus delta for delta greater than 0. Now by mean value theorem, if I apply mean value theorem, now by mean value theorem, we get mod of fu minus fw is equal to mod of f dash of c into mod of u minus w. This is my mean value theorem. Means there exists some c in that interval I such that mod of fu minus fw is equal to mod of f dash of c into mod of u minus w. But mod of f dash of c is less than or equal to alpha. So I will get it is less than or equal to alpha times u minus w if u comma w belongs to interval I. Is that okay?
Yes, ma'am.
Now for each u in I, what is fu minus v? V is a fixed point of f. So what is f of v? V can be written as f of v. I can write like this, since v is a fixed point of f. So that is fv is equal to v. So fu minus v I can write as mod of fu minus fv, but which is less than or equal to alpha times mod of u minus v, right? And we are saying it is less than delta, which is less than delta because all points are in this I, interval I. What is that interval? V minus delta, v plus delta. So there must be which is less than delta. So this implies fu is in I, and if I say fu is in I, this implies v is stable, right? All points near to v means all points near to v, we are saying they do not wander from v under all iterations of f. So we are saying v is stable. Now we want to what we want to show, it is asymptotically stable. So for asymptotically stable, we have shown first it is stable. Now we will show additional condition, convergence. So furthermore, consider mod of f raised to t plus 1 at u minus v. Again, how I can write this? F of f raised to t at u minus f at v. I can write because v is a fixed point again. Can I write like this?
Yes, ma'am.
Yes, ma'am. Now f of something minus f of v must be less than or equal to alpha times mod of f raised to t at u minus v for each t greater than equal to, for this is for each t greater than equal to 0. Now again I can write this as f of f raised to t minus 1 and again this v I can write as f of v. So I will get this is less than or equal to alpha square mod of f raised to t minus 1 at u minus v. Is that right? Is that right?
Yes, ma'am.
Yes, ma'am. Now again, so if I go on continuing, you can for each t greater than equal to 0 and u belongs to I. Now, so by induction, if I go on repeating this, we will get alpha raised to t mod of u minus v. Okay.
Yes, ma'am.
Yes, last I will get fu minus fv. Fu minus fv I will get. So alpha will be outside alpha raised to t mod of u minus v. That is mod of f raised to t u minus v is less than or equal to alpha raised to t times u minus v for t greater than equal to 0 and u belongs to I. So what this says? What is my alpha? Alpha is strictly less than 1. Since alpha is strictly less than 1, what I will get? Limit t tends to infinity, alpha raised to t should be what? What should be this limit? It must be 0. It must be 0. Since alpha is less than 1, limit t tends to infinity, alpha raised to t is equal to 0. So this implies each solution of equation that originates in I means that starts in I converges to V as t tends to infinity, and this implies V is asymptotically stable. The points near to V. So what is my I? I is my V minus delta, V plus delta. So it is an open ball centered at V, radius delta, V minus delta, V plus delta. So we are taking all solutions which starts in I, converges to V as t tends to infinity. Therefore, we can say that V is asymptotically stable. Is that okay?
Yes, ma'am.
Yes, ma'am.
Now we will prove
Yes,
B part. In B part, we have to assume mod of f dash of V is strictly greater than 1. So assume that mod of f dash of V is strictly greater than 1. So in this case, we want to show V is unstable. So if mod of f dash of V is strictly greater than 1, choose lambda strictly greater than 1 and I is equal to say V minus epsilon, V plus epsilon for some epsilon greater than 0. So that what is my Fu minus Fv? Fu minus Fw we will say. It will be again by previous theorem f dash of c times mod of u minus w, and my mod of f dash of c is strictly greater than 1, so I can write this as greater than equal to lambda times mod of u minus w for all I, for all u and w where u and w belongs to I. Now again by induction, what is f raised to t at u minus v? Same, if I apply, it will be strictly greater than equal to lambda raised to t mod of u minus v, as long as f raised to t at u belongs to I. But what is my lambda? Lambda is strictly greater than 1. Since lambda is strictly greater than 1, it follows that all solutions which originates in I, which starts in I, except for the constant solution, u at t to v must leave I for sufficiently large t. So this implies V must be unstable. V is unstable. This condition, since lambda is strictly greater than 1, we can say that all solutions leaves I, or they wander from I. They goes from far from I. Okay, so V must be unstable. Okay, so whenever we want to check V is asymptotically stable or unstable, so it's better first find its first order derivative, check whether it is less than 1 or greater than 1. If it is strictly less than 1, you can say that it is asymptotically stable. If it is strictly greater than 1, you can say that it is unstable. Is that okay?
Yes, ma'am.
Yes, ma'am.
So now we will take example. Check stability of fixed points for the functions first function is fu is equal to 2u 1 minus u. So if we want to find a stability of fixed points, so first we need to find its fixed points. Okay, so what are the fixed points we have already calculated?
Half and 0.
half and 0. We already, or shall I write? First we find its we find fixed points of f. So consider fu is equal to u, that is 2u 1 minus u is equal to u. This implies 2u minus 2u square minus u is equal to 0. This implies u times 1 minus
2u is equal to 0.
is equal to 0. This implies u is equal to 0 or u is equal to 1 by 2. So therefore 0 and half are the fixed points of f. This already calculated. Now we want to check whether they are, what is the stability, whether they are asymptotically stable or unstable. So for that we will find, to check stability, by above theorem, let's find mod of f dash at u we are saying no, u is equal to 0. What is mod at f dash at u? What is f dash at u? If f of u is 2u 1 minus u,
2 minus 4u.
2 minus 4u. 2 minus 4u. So at that point, what is f dash at 0? So at that fixed point, what is mod at f dash at 0?
2.
Is 2. So and what is mod at f dash at half?
0.
2 and minus 2, so 0. So 2 is strictly greater than 1 and 0 is strictly less than 1, right? So this implies, what this implies? 0 is unstable, and what about half? Half is asymptotically stable. Is that right? 0 is unstable fixed point and half is asymptotically stable fixed point. Is that okay?
Yes, ma'am.
Let's take second example. Fu is equal to cos u. So what are the fixed points? Fixed points of f are the solutions of the equation. Which equation? Fu minus u is equal to 0. That is cos u minus u is equal to 0. Right?
Yes.
If I want to find fixed points of f, means fu is equal to u, it must satisfy. So cos u is equal to u. Which are the points? So the points u which satisfies cos u is equal to u. So if I solve this with numerical analysis, this gives me fixed point is 0.739. Using numerical analysis we want to solve, because this is a non-linear equation. Okay, so fixed point for this is 0.739. So approximately, again this is approximately we can write 0.739, because in with numerical analysis, numerical computations, we are not getting exact solution, but we are getting 0.739. So now we want to check whether it is stable or asymptotically stable. So for that we will find, to check stability,
मॅम
yes,
मॅम फिक्स्ड पॉइंट तिथं -π/2 येत नाही का?
minus
π/2
π/2. Cos π/2 is what?
0.
It's not π/2, no?
मॅडम पण तिथं
I want value of u for which cos u is equal to u. Cos π/2 is not π/2, so it is not a fixed point. So we have to solve this by numerical methods, like bisection method, or Newton-Raphson method also we can use to solve this equation. But here not necessary, we just write fixed point is this one, 0.739. You can check with any numerical method. Okay. So to check stability, what I need to check stability, we find what is mod of f dash at u. What is f dash at u? If fu is cos u, what is f dash at u? It is minus sine u. So mod of f dash at u is whatever may be your u, it is equal to mod of minus sine u, and we know that it is strictly less than 1. Yes, sine function,
yes
whatever may be your value of u, it must be less than 1. So what can I say?
asymptotically stable.
It is asymptotically stable. Therefore, the fixed point V, which is approximately we are saying 0.739. If you don't write also no problem, is asymptotically stable. We want to just check its stability, asymptotically stable. So we will directly calculate mod of f dash at u, and since it is sine u function, we can say it is strictly less than 1. So the fixed points V must be asymptotically stable. Note that remark, we can say, one, theorem 4.17 can be used to check the stability of periodic points because in periodic points also that w, f of w, they will be acts as a fixed points of f raised to k. Okay, so 4.17 also can be used to check stability of periodic points. For example, suppose if v is a point of period 2 for the function f, by chain rule and theorem, using theorem 4.17, V is asymptotically stable if mod of what is it is period is 2, so f square and its derivative at V. This I can write as mod of f dash at f at V. At V into f dash at V. And it must be strictly less than 1. This is by chain rule. We can, if I apply f dash at f at V into f dash at V. And second, this also implies that the periodic point Fv is asymptotically stable. And third, similar remarks apply to the points with higher periods. So can take one exercise. Uh, 4.35 and 4.36. Test the stability of the fixed points of the functions first f is equal to u square, p f is equal to u cube, third one c is equal to 3u plus 2, and d minus u plus 1. So first you have to find fixed points and then you have to check whether they are stable or asymptotically stable. And another example is show that the function f is equal to 1 by 2 times u cube plus u has one asymptotically stable fixed point and two unstable fixed points. Two unstable fixed points. So first you need to find fixed points. Since it is cubic, you will have three solutions of this equation. Okay, so that three will be fixed points, and in that if you calculate mod of f dash at u, one will be strictly less than 1, and for remaining two points it will be strictly greater than 1. So they will be unstable fixed points. Okay. So you can check this. And we will stop here. In tomorrow's lecture, we will see Lyapunov function to find again to check the stability, another criteria to find the Lyapunov function. Is that okay?
Yes, ma'am. Yes, ma'am.
Download the attendance.